So far we've used two methods to solve a set of simultaneous equations. First we solved a set of simultaneous equations graphically. Then we used technology to solve a set of simultaneous equations. Now this is going to be the third method we're going to use, where we're going to use substitution to solve a set of simultaneous equations. Now we could use any of these methods to solve the equations, and if we do them properly, then we'll always get the same values for x and y, whether I solve by substitution, or whether I solve graphically, or whether I use my calculator. So here we have our set of equations again. One is in gradient intercept form, the other is in general form. So if I come over to my graph paper, you can see I've just copied the two equations out. So basically, all I'm going to do is, if I have two variables in one equation, it's not helpful for me. I'm not able to solve for those unknowns. However, if I substitute my value of y, which is x minus 3, into this equation here, you can see I only have one unknown variable, and that will allow me to solve for my unknown variables. So what we say is we substitute one into the other. So you can see I've labeled my two equations. This is equation 1, and I've called this equation 2. It's very important to label them so then you can communicate your work clearly. So I'm going to start off by substituting my equation 1 into 2. So I'm going to substitute this bit here into this equation. So I've got 2x plus 3 by, now rather than putting the y, you can see y is equal to x minus 3. So I'm going to substitute the x minus 3 into here. So all I've done is substitute that for my value of y. So you can see everything else is the same. So it should be equal to the 16. Now it's just a matter of simplifying the left-hand side of my equation. So I need to expand these brackets, collect like terms, and then solve for my unknown value of x. And then I can use that value of x to find my value of y. So my 2x is going to remain as is. Now we have to use the distributive law to expand these brackets. So I'm going to go 3 times the x, which is 3x. And then 3 times negative 3 is minus 9, is equal to 16. And now it's just a matter of, like I said, collecting like terms. So 2x plus 3x is 5x. Minus 9 is equal to 16. Now I'm trying to isolate this x. So to get rid of this minus 9 from the left-hand side of the equation, I could add 9 to both sides. So I would be left with 5x here, and this would be equal to 25. And then to get x all by itself, all I need to do is divide both sides by 5. So if I divide this by 5, we would have 5x over 5, which is essentially just 1, so we've got 1x, is equal to 25 divided by 5 is 5. So I've found my value of x. Now, what I can do is I can now substitute this value of x into my equation here to find my value of y. So if we come over to this equation, you can see they've found that their value of x is equal to 5. And now they're going to substitute that value into equation 1. So substitute x is equal to 5 into, I'll just keep consistent with what they substituted into equation 1. We could substitute it into either equation. It doesn't actually matter, but I'll keep consistent with them. So we're going to substitute our value of x is equal to 5 into this equation here. So we're going to have y is equal to 5 minus 3, which is equal to 2. So therefore, the solution is x is equal to 5, y is equal to 2. And then they do a check. So all they do is, if they want to check that this solution is correct, if we substitute those values into our first equation, so we just said that y was equal to 2 and x was equal to 5. So y is 2. If I substitute x is equal to 5 here, you can see 5 minus 3 would be 2. So 2 equals 2. So that checks out. Or you could substitute the value into the second equation as they've done, and you'll find that 16 is equal to 16. So therefore, they've checked that their solution is correct.